In this problem, we are going to apply the Ampere's law to solve and get the value of or the expression for the magnetic field. So here we have got a cylindrical wire of radius r, and it carries a steady current I directed out of the page, which you can see is shown by the dots. So the current is directed out of the page and it is uniformly distributed through the cross section of the area. So it's uniform distribution of current throughout the wire. According to Ampere's law, the current creates magnetic field both within the wire and outside the wire. Derive an expression for the magnetic field at a point which is at a position r, small r, greater than capital R. Small r is the radius of our Amperean loop and capital R is the radius of the wire itself. So let's just get that straight first. So small r is the radius of Amperean loop and capital R is the radius of the wire. Now we are going to apply the Ampere's law to solve this. So let's see. Let's write down the Ampere's law. B dot dl is equal to mu naught I, where I is the net current in the Amperean loop. So our Amperean loop, as shown in the diagram, this is our Amperean loop. Because R is greater than capital R, so we can see that the Amperean loop is outside the wire. So the wire itself is enclosed in the Amperean loop. So all of the current is going to be considered when we apply the Ampere's law. So that will be closed integral B dot dl equal to mu naught I. So we are not going to change anything to I. We are going to write I as it is. We can write here I net, and in the second step it will become mu naught I. Now we want to solve this closed integral. So B is going to be constant. It will come out. Closed integral dl equal to mu naught I. Now when we do the integral of dl, what does that mean? So dl is actually a small length of the Amperean loop. So if I do the integral of dl, I'm going to get the circumference of the Amperean loop. So dl, which is the circumference of the Amperean loop, will be equal to 2 pi small r. So from here we can write B multiply 2 pi small r equal to mu naught I, which we can rearrange and we can get the magnetic field as mu naught I over 2 pi r. So that's the expression of magnetic field for a point which is outside the wire. Now next we want to consider the circular loop within the wire as shown below. Now the Amperean loop is inside the wire. What is the current enclosed in the circular loop? So we know that in this Amperean loop, we are not going to get all the current which was passing through the wire. Only the current which is in this area or in this region has to be considered. So it's first asking us to find the current enclosed in the circular loop that is centered on the wire's axis and has a radius r less than r. So for that, we are going to use our unitary method. So I'm going to make two tables here, area and the current. So for the total area, which is pi r square for the wire, the total wire, the area is pi r square. So for pi capital R square, the current, let me write this as I net, the current is I itself. That's the current which is passing through the wire. And for the area which we want to find out, that is the Amperean loop's area, we want to find what's the current. So we are just going to find by unitary method. So I'm going to multiply this way and divide this way. So I enclosed will be equal to I multiplied by pi r square over pi capital R square. So that will be I small r square over capital R square. That's our I enclosed. Now it's asking us for what is a magnetic field at the position r less than r. That means at this position, that is inside the circle. So we go back to our Ampere's law. B dot dl equal to mu naught I net, which is the same as I enclosed. So B is constant, B can come out. Closed integral dl mu naught and I net, which is the net current in this Amperian loop, which we found here. So we'll replace that here. I r square over r square, and dl we already got here. Closed integral dl is 2 pi r, so multiply 2 pi r equal mu naught I small r square over capital R square. We can rearrange this equation. Mu naught I, okay, small r square, capital R square, 2 pi r will come down. We can cancel out the small r's. One of them will get cancelled out. So mu naught I r over r square multiply 2 pi. Okay, I can just write this. I'll just write this here just to get it in a proper form. Mu naught I 2 pi r square, these are all constants, multiplied by small r. Okay, now next is asking us to sketch a graph to show how magnetic field varies from the center of the wire out. That means from the center of the wire as you move out, how is the magnetic field going to change? So when you are inside the wire, we have to use the expression which we got just now for r less than r. When you are outside the wire, we have to use the expression which we got here for the first part. So our we have to set r, that is the radius of, like we have to fix the radius of the wire, the real wire, on the axis, x-axis, because at this point we are going to get a discontinuity. So this is r less than r and this is r greater than r. That means small r less than r, small r greater than r. Small r is for the Amperian loop, capital R is the radius of the real wire. So I'll just write the expression here. Let me change the color. So r less than r, we got B as mu naught I 2 pi r square multiply small r, and for r greater than r, we got it as mu naught I over 2 pi r. Okay, now let's check. So as r increases, magnetic field has to increase. So in this region we should have a straight line. It's a linear relation, so we'll have a straight line like this. But for r small r greater than capital R, we can see it's an inverse relation. As r increases, b has to decrease, and this inverse relation will be a curved graph. We have done this before also, so it will be something like this. You'll have a curved graph.